Welcome to the class again. You already have been given an input on how to design sieve trays. Today's session starts on designing of bubble cap trays. In fact, it's not only the trays, it has to cover the bubble cap tower itself, which is not very different from the other types, but let's move on with that. First, we see one thing, that in case we have to design a tray, the basic inputs that are required are the vapor and the liquid related items like the flow rate, the density, the viscosity and the surface tension. These are the 4 things that you require. And if you are talking about the deliverables, there will be 2 sets of deliverables. The one set will be the process parameters, for example, percentage flooding, percentage approach to flooding, tray efficiency, entrainment and such things. And you will also be delivering quite a good amount of mechanical details, which includes the bubble cap type. In fact, you do not manufacture normally bubble cap type, you specify the type, their dimensions, the slot details, their size, the number on each particular tray. If you are having a tray which is sufficiently large, it will be built of segments. Quite naturally, you have to provide the tray layout showing the location of the caps, basically the vapor dispersers in this case. You have to provide the wear heights, possibly you will be having a single wear at the outlet, but in case you require, you may have an inlet wear also, that also we have discussed earlier. You have to discuss and give the details of the downcomer, the type and its dimensions. You definitely for the tray has to specify the tray spacings, which is expected to be different in the feed tray top section and the bottom section at least. There will be different tray spacing when you have your manhole for man entry as well. These will belong to the tower. You definitely have to give out or specify the nozzles, their size, orientation, elevation at which they are to be on the shell. You have to provide the manholes, the same thing about it, that means the orientation and elevation and the size. You have to give certain specific dimension on the trays, for example, the clearance of the downcomer from the tray deck. You definitely have to specify the elevation of the column bottom as well. The elevation of the column bottom depends on how you are going to take out your material. Basically, it is required to provide the minimum required NPSH for the bottom material to be pumped out. So, these are the list of deliverables in case of any sort of tray tower design. Let us have a look at the bubble cap first. The cap portion is this. This is the cap. The different, and this cap is basically mounted on a riser. It is basically mounted on a riser. This part you can forget. The vapor goes up this way, comes out through the slots and bubbles up. The mechanism of working we have seen, but let us see, in order to function properly, there are certain essential things that has to be obeyed. The first thing, there has to be submergence of this. That means, your vapor disperser has to remain submerged, so that only the bubbles come out and the interaction is between the bubble and the pool of the liquid which is surrounding it. The cap has got usually either trapezoidal or square. It could be square also, it could be something like this. I meant rectangular, this type of slots. The vapor comes out through these slots. So, quite naturally, the liquid level in the slot will get depressed to a particular level like this, up to this level. So, this part of it is vapor, this part of it is vapor, and below that it is liquid. So, there is something called slot submergence. The top of the slot definitely has to remain under the liquid level all the time, and when there is no flow, the minimum level of liquid is the outlet wear elevation. It's the outlet wear elevation. So, quite naturally, this is the static slot seal. That means the minimum level of liquid above the top of your slot. Now, in case of the flowing liquid, quite naturally there will be a level of liquid over the wear, and above the cap itself there will be some amount of liquid, and from here up to the top of the slot will be your dynamic slot seal. Similarly, if you look at the bottom of your slot, you will find that there is a rim. There is a solid rim which is called a shroud. It is called a shroud ring. The shroud ring typical thickness is around 6 millimeters, quarter of an inch. You will also note one thing, that means whenever you have this type of slots which are wider at the bottom and narrower at the top width is roughly half of what you have at the bottom. You can also have triangular slots, but those are not very common. I believe with this we will go further and have a look at the functioning of the bubble cap over the zone of liquid flow rate and the vapor flow rate. This is absolutely very similar to what you have seen in case of the other disperser, which you have seen, which is basically your sieve tray. What you find that in this case also you would like to maximize, you have a zone of satisfactory performance. Your satisfactory performance is possibly in this zone, and quite naturally if you would like to have minimum number of caps, you would prefer to have your design operating in this zone with a fairly high amount of vapor flow rate as well as a liquid flow rate. This would make fewer number of bubble caps necessary for your tray. I am not going into the details of the malfunctions. Many of these are very obvious. For example, if you have a very high flow rate, your slots will open 100%, and if you increase it further, there is no scope of opening further amount of the slot opening. So, what happens is you have almost a jet of vapor which is coming out through your slot, which will reduce your contacting quality. So, you do not want to overload your slots, and you would like always to operate below your overloaded slot limit. It will also lead to excessive entrainment, particularly if you have a low liquid rate and a high vapor flow rate. You will have insufficient slot submergence with lower wear height if you have a low amount of vapor rate also. So, you have poor vapor distribution in this, and you have dumping as well. So, we know now that our preferred zone of operation is here with a fair amount of flow of vapor and the liquid, both tending to be high. Now, there is something. If you are making a column, tray spacing directly influences your total height of the column, that means the column cost. Typical tray spacing lie between 450 and 750 millimeters. Most common is in fact 600. Typical standard values are 450, 600, 750. You can have lower tray spacing also, particularly in smaller columns. The tray spacing, it is not that if you reduce the gap between the trays, the chance of entrainment of liquid along with the vapor which reaches the upper tray, it comes to, if you goes up, if you have a lower tray spacing, If you have a lower tray spacing, the chance of entrainment would go up, but there are quite a few other things on which your tray spacing would depend. In large diameter columns, more than 1.5 meter diameter column, the tray spacing is normally kept 600 onwards, because in order to fix the trays, someone has to go in and crawl between the trays. For inspection also, he has to go in over there. For smaller diameter columns below 1.2 millimeter, typical tray spacing could be 450. It may not be necessary to crawl between the trays and narrow towers, because it is accessible from outside if you have a proper manhole somewhere. In cryogenic columns, the tray spacing is typically low. I have mentioned that if you have a lower tray spacing, the chance of entrainment is less. The chance of entrainment is more. In case of the oxygen plant, that means in air separation plant, the liquid has got a very low surface tension, and naturally the chance of entrainment is very low, and people have gone for very low tray spacing as low as 75 millimeters. You have a very big advantage over there. That means, if you have a low tray spacing, you have a lower height of the column, and cryogenic columns have to be very heavily insulated, and so naturally if you have a lower tray spacing, lower exposed surface, and your heat inlet to the system is also low. Whenever you have a draw-off tray, which is a chimney tray, or a feed tray, or a reflux entry, you normally will be having or requiring a minimum of 750 millimeters of the tray spacing, or it will be at least 1.5 times the tray spacing. Now, if your typical tray spacing is 1200 millimeters, you usually will be in a position to provide around 20-inch manholes, and in tall trays you require at least a manhole after 8 to 10 number of trays. The tray spacing above a chimney tray, the standard is to keep 1.5 meters tray spacing. That means, from the chimney tray to the tray upper one, the gap should be about 1500 millimeters. The top dome of your column, from the top basically up to the tangent line, I had explained what exactly is a tangent line in the last interaction session, should be minimum of the double of the tray spacing, or it should be 1200 millimeters from the top tray deck minimum. Sometimes the tray constructions and the tray spacing is also limited for indoor installation, where there is an existing shed and there is limited headroom. So, these are the basic considerations for deciding the tray spacing, but by overall you will have an idea that tray spacing in industrial columns will be of the order of 600 millimeters. Higher ones will be required for the draw-off, feed tray and reflux entry, and for providing manholes every 8 to 10 trays. Now, we need to find out the diameter. There are two techniques of finding the diameter of bubble cap trays. The first is proposed by Souders and Brown. This is a very standard and a classical procedure. The procedure basically depends on, or rather relies on, an empirical relationship of estimating the MV bar max. The MV bar max is basically the maximum allowable vapor mass flux, and you will notice one thing I have put in bold, that it is based on the total tower area, it is not the active area. So, your Souder-Brown's equation is based on the total tower area, which is a capital D. Quite naturally, if I know my mass flow rate of vapor and if I can estimate my maximum allowable vapor mass velocity, if I divide these two, what I get is the tray area, and from there the expression of d is nothing, it is just geometry. The basic thing, the most basic empirical thing which is used here is the constant C and another constant which is given here. You will notice one thing, it is rho v multiplied by rho L minus rho v, it is not rho v upon rho L minus rho v. And the C is an empirical constant which it depends on this k chord factor which is given here depending on the application. It is to be corrected for sigma, the surface tension of the liquid. You will notice one thing, if surface tension goes up, C goes up, your allowable mass velocity goes up, your diameter comes down for the same mv. Now, in order to evaluate C, C is basically a function of the tray spacing as well. So, what you have here is the different tray spacing that are standards. The expression of C is here, and this is found out from the values which is given here. So, what you have here is the value of C which you find from here, which you ultimately get from your k chord, correct it for sigma, evaluate the mv max and then find out the diameter. I have a question here for you, why should the column diameter depend on Ts? We see here the relationship makes it definitely dependent on the Ts. Basically, they are related in this way. If you see, if I have a very narrow column with a small d, my chance of entrainment is more. But if I have to have a reasonable amount of tray efficiency, I must have a larger Ts. That means, if I have for my service a larger diameter tower, possibly I can go for a lower tray spacing, and the vice versa is also true. So, that is the answer. The Souders-Brown method is based on the design of standard bubble cap tray design and layout. The C factor may vary along with the tower and needs to be estimated for the top, bottom and the intermediate position, so that the maximum diameter required in a particular section is determined. And normally that is the tower diameter which is kept for the other trays, which may or may not require blanking of certain of the vapor dispersers. Now, I reiterate that the mv max term is based on the total tower cross section. It is not the active area or any other the net area as in other vapor disperser designs. Now, to take care of uncertainties in the design conditions, D may be divided by a factor of 1.05 to 1.25 and arrive at a conservative tray diameter. I have made a mistake here, I would like to correct it, is to be multiplied. That means, you generate a higher value of D, which will lead to a lower entrainment and a better fractionation. The factor can be 1.05 to 1.15 for towers operating in the pressure range 0.35 to 1.217 kg, or normally the value is taken higher for vacuum towers. The other method for designing is from Fair and Matthews. In fact, you should refer to the book design of equilibrium stage processes by B. D. Smith, where the procedure is written by Fair himself. Fair defines a factor FLV. His definition is based on the flow rate, the mass flow rates and the densities related this way by this expression. Then what he does, he finds out another constant CSB. SB definitely stands for Sauder-Brown, but he never mentions it anywhere, at least in this stage. And for different tray spacings, the constants for finding out the CSB are different. Once the CSB is available, based on the CSB and the value of the densities and the surface tension of the liquid, and also another parameter J, which is basically the tray efficiency, the value of J is the approach to flooding, basically percentage approach to flooding. The conservative value of UVN is found out, which is used in finding out the diameter. UVN is used in this expression, and this expression gives you the volumetric flow rate of the vapor, from where you find out the D. So, this is how you find out the diameter by following the Fair and Matthews procedure. The steps of calculations in this case are the compilation of the inputs, computing the FLV value, corresponding to FLV estimating the CSB for a chosen TS. We will note that here that the CSB values are different from the C of Sauder-Brown equation. C considers negligible entrainment and involves a total tower area for calculation. This is the major difference what you have. That means, C is based on the total area of calculation. This is as per Sauders and Brown, whereas in this case it is not meant for that. It is based on the net tray area, which has already been defined to you as AN, which is for a single pass tray is equal to A of the tray minus A of the downcomer. That means, this basically is the area which is available for the vapor to approach the upper tray. So, it is the net tray area which is used. Typically, the approach to flooding is around 70% or 80% for higher diameters. We already know that the wear length typically which is taken is about 76 to 78% of the diameter, which makes K, which is a correction for the downcomer area, to be around 0.12 or rather 12% here. So, your D is given by this expression which is there in the previous slide as well. It is customary to check the diameter for the top tray, bottom tray and the feed tray, and adopt the largest of the D as a tower diameter. Normally, varying a tower diameter at different elevations is uneconomic, because it involves a good amount of increase in the manufacturing cost, but in case of very large columns like the crude columns, it is done. The crude column typically will have a narrower top and a bottom section and a fatter middle section. The Fayette's correlation is about 15 plus minus 15% accurate, and the basic correlation is for sigma is equal to 20, and we already have told you about the correction if the deviation is from sigma is equal to 20. The bubble tray where height should be below 15% of the tray spacing, which is very common. I mean, in most of the cases you will find that the wear height will be something around 50-60 millimeters, whereas your tray spacing is much higher. Bubbling area covering most of the area between the wears. When the TS is smaller, the height of the two phase, which is the froth plus liquid layer and not the blow off process, is decisive for the highest feasible gas load. For safe operation, the froth level must always be less than TS. Now, flooding may be on tray, which is by the entrainment flooding, or it could be in the downcomer, which is called downcomer flooding, and it has already been discussed when the other type of vapor disperser has been told to you. So, in order to complete this, what you further require is to check for the entrainment. That means, you have found out already the diameter, you have decided on the tray spacing. Now, let us see what all things are still left. We have to find out the percentage entrainment and its effect on the efficiency. You have to find out the slot opening under operating conditions. The liquid gradient on the tray has to be evaluated. The downcomer, the procedure to evaluate the downcomer is already told to you in the when the vapor disperser of your sieve tray has been covered, and you are to supposed to estimate, we need to find out how to estimate the pressure drop across the tray, and definitely we have to decide the outlet well length and height. This we will be covering in the next class. Thank you.